Right, so good afternoon, everyone. First of all, I'd just like to say thanks to the organizers, Professor Ren and Professor Bao. So I thought what I'll do today is to tell you a little bit about what my group has been doing maybe for the past three years or so, looking at problems involving ternary fluid systems. So this is either where you have 3 liquids or 2 liquids and a gas, okay? And then I think giving the last talk of the day is always quite hard. So I'll switch gear a little bit. So I'll show you lots of examples, lots of applications, so lots of movies, so bear with me. But the workhorse is actually something called the Lattice Boltzmann method. I'll tell you a little bit about the Lattice Boltzmann method, but if you have questions, then feel free to ask me either during the talk or later or tomorrow. Okay, so this is the plan of the talk. So I'm a physicist, so usually when we do things, we are driven by the problem, so the physics. So I'll probably try to motivate the talk by giving you maybe 5 examples why ternary systems are exciting. I noticed that there are lots of good methods being developed, so maybe this will be something you would like to do in the future. And I'll tell you a little bit about the method that we use. And then I'll pick just 2 examples from this ternary fluid system where I will expand a little bit. So the 2 cases I will tell you is collisions of immiscible droplets and also drop dynamics on liquid infused surfaces. And if there is a bit of time, I might tell you recent work that we have done for contact line slip in simple diffuse interface model, simply because there are lots of talks in this area, so I thought I'll share a little bit. But if there is time, if not, just ask me. Okay, so motivations, examples. So the first one I'll tell you is the problem where you have drop collisions. So lots of people have studied drop collisions, but typically this is between 2 droplets of the same kind, right? So we want to do something a bit different. So we're looking at 2 droplets. They are both immiscible. So you can think about water and oil or different types of oil. And then if you look at that example, it turns out that the behavior is extremely rich. So these are just 3 cases out of actually 5 or 6 different scenarios you can see. So in the first case, you see that the 2 droplets come together and then they just bounce, right? And in the second case is they come together and they start to coalesce. But they coalesce in the way that one of the droplets is encapsulating or eating the other droplet, right? And in the third example, they do something similar, but because of the surface tension and so forth, it doesn't do that. It actually just basically come and then it just adhere with each other, so they doesn't get encapsulated. So the second example that I will tell you is to do with liquid infused surfaces. You've seen quite a few of these things on the first day. So this is the work that David Kere has done, and also Daniel. These are some beautiful surfaces inspired by these pitcher plants. So I think David Kere showed a different version of this movie, where if you have a pitcher plant and it's actually quite wet in the surrounding, the ants are miserable. They are being eaten. Now, these are the biological examples. So you can also think about, well, now that we have the surfaces, what can we do with it? So this is one case. So there's actually a company that makes these things. So I'm sure you have this problem with your ketchup bottles, where if you are at the end of the day, you try to pour your ketchup and it actually stuck, right? So there are many strategies that have been proposed. But if you have these liquid infused surfaces, also sometimes called slips, you probably don't have this problem, which can be quite good, right? So this is just in the context of ketchup, but of course there are many packaging problems that you can think of where it can be quite useful. So in this context of this talk, so I'll talk a little bit about this example. This is the typical setup that I would like you to keep in mind. So typically we have a liquid droplet, and it's sitting on top of these liquid infused surfaces. It's corrugated, but the corrugation is infused by another liquid. This is typically some wetting oil. Okay, this is the second example. Third example, phase separation. So I think many physicists like phase separation. I've seen quite a few movies, but typically this is the case where you have binary system. What happens if you have ternary system? It turns out, I think there are many nice examples you can actually watch forever. So this is the case where it's the composition is equal. So a third, and a third. And if you do that, this is what I typically call the glass pane window morphology, where it kind of likes a droplet, and the way they coarsen actually looks a bit like foam. So I was having a nice discussion with David, which is, I think, not here. So this is just a third out of a third. What happens if you just simply change the composition and keep everything else the same? right? So this is simulation, yeah. So if you just basically keep the composition so that, let's say, the third fluid is very little, you see something very typical of the binary system, but then the third fluid kind of goes at the interface and it then forms droplets. If you actually change the composition once again, this is C1 equals to C2, but the sum is less than C3, you basically get what I call double spinodal. So you see that there is a phase separation, and then these droplets then phase separate again. Right? So I think there are really amazing morphologies to be studied, and what is interesting is that if you're thinking about like polymer phase separation, this is actually potentially quite common. And this is quite complicated, and there are many things that we can still study. So all I have done here is just changing the composition. So we still have problems where we change the viscosity, we change the surface tension. So it's potentially a very rich problem. Okay? And this is also 2D, not 3D.
Just to know, the surface tension here is the same.
It's all equal, yeah. So we just take the simplest example, but you can do many things, yeah. The fourth example I would like to tell you is in the context of microfluidics. So microfluidics is quite popular these days. This is a way, for example, here to make complex emulsion, so droplet inside droplet. So if you're talking to people from synthetic biology, sometimes this is a way to encapsulate cells. And then this is how they actually try to isolate the cell and study there. And what I've shown you here is that by simply changing the surface tension, for example, we can get very complex behavior from what we call double emulsion, complex emulsion, to a Janus droplet. This might be interesting for self-assembly, whereas if you change the surface tension, so this is non-wetting, you see that the droplet gets expelled. Okay, now the fifth example, this is the last example to motivate you why this is an interesting topic, is something to do with what the community called Boyce-Lock self-propulsion. So this is actually what David Kere did, 2002 or so. He basically put two oils in a capillary, and he just leave it there, and then the whole system starts to move, right? And it just continues to move. Would any of you like to guess why that could be? So this is a bit strange, right? So you just put two oils and it self-propels. Any guess? No? So if you have a normal system, it wouldn't, right? Because where does the energy come from? So the secret is that these oils are actually in what we call the pseudo partial wetting cases. So what that means is that it looks like it forms a finite angle, but actually there is a bit of oil wetting here and over there. So this is very similar to the case that Shahriyar was showing in his simulations. So in that case, actually, the surface tension between the third phase and this bit of solid is different from this bit of solid. This is basically what's giving you the energy. So it's self-propelling. If you're a surface science person, there is actually a relation called the Good-Giri-Falco relation. That is actually the case where the Good-Giri-Falco relation is actually broken. So the three contact angles are actually not independent in a typical system, but if you have some funny system like this is broken, and you can get the self-propulsion. Okay, this is what happens, for example. You actually get self-propulsion. Okay, so those are different examples that we can do. Now I'm going to tell you how we're going to tackle the problem, and what we do is use something called Lattice Boltzmann method. So in the Lattice Boltzmann community, I think no one has actually talked about Lattice Boltzmann here, but one of the challenges in Lattice Boltzmann community is to actually think about how do you introduce multiple fluid components, in particular if you actually introduce more than two. So we're thinking about 3, 4, and so forth. There are several schemes that people have developed called the color, Shanchen, and free energy, which is very similar to the phase field method. And then I'm going to choose this method. So what that means is that the model I introduce is applicable if you want to solve it with any other method. I'm just solving it in a different way. And then the equation of motion in the continuum level is, of course, not surprising. I'm solving the continuity equation, the Navier-Stokes equation, and the Cahn-Hilliard equation. So if I have two components, I have one Cahn-Hilliard equation. If I have three components, I have at least two, and so forth. Yeah, so it's just basically counting. Now, if, let's say, I take the simplest case where I have three fluid components and the density is equal. So let's start with the simplest example. So one model that we can propose, and we're not the first one, Probably Boyer and La Puerta was the first one, if they're not, apologize. So what they have proposed is that, let's say you have 3 fluids, and then one way to do this is by simply introducing several double well potentials. So you can see there are 3 of them corresponding to each of the bulk phase. And then this term tells you that there is a minimum at C1 equals to 0 and C1 equals to 1. Right? So it's very, very simple construction. So what that means is that if you take, let's say, a constraint where the sum of the composition is 1, there are 3 bulk phases corresponding to the first fluid, the second fluid, and the third fluid. Yeah, so very simple. And then this term here, the gradients, are there to give you surface tension. So very similar to the binary case. So the structure of the equation is very similar. Now, I would like to give you a graphical interpretation of this equation, because that will be quite useful for later on. So if I simply choose 2-order parameter to describe my ternary fluid, and in this case I have chosen phi, which is C1 minus C2, and psi, which is C3, you can think of this equation as basically an energy landscape where there are actually 3 minima, and they simply correspond to C1, C2, and C3. Right? And then the nice thing about this system is that, if you put in the interface width and you choose the value of kappa, the surface tension is actually analytical. Okay? So we've done our homework and we test the Neumann triangles, for example. This is one thing you can do to test what happens if you have ternary system. The surface forces should actually balance at this contact line. And then it basically follows this sine law, or you can call it a Neumann triangle. And you see that our implementation reproduces the Neumann angle quite accurately. Rho? The density? Yeah, so this is equal density, so the density is the same everywhere. So in the second part, actually wait for 2 slides, I'll tell you how we introduce density ratio. Yeah. Okay, so this is basically introducing surface tension in the system. How do we introduce wetting contact angle? There are several ways. So one way is to introduce another free energy term, and the simplest one you can choose is a linear term. So for example, this is telling you that there is some sort of interaction between the solid and fluid 1, solid and fluid 2, solid and fluid 3. So if you choose this linear term, typically you get good prediction up to basically within the range of maybe 25 or 30 all the way to about 150. You can actually do a bit better if you choose a cubic term. There are some nice properties there. I'm not going to discuss the details. So that's one way. Another way that we typically do it is using something called the geometric boundary condition. So this was first introduced by Ding and Spelt in 2007. And the idea is extremely simple, because we know that we have a diffuse interface model. So if you imagine that this is a droplet of C1, so therefore C1 is around 1 here, and C1 is 0 outside. If you think about the gradient at the interface, it basically has a gradient that goes that way, right? And then what they say is that if you want a certain contact angle here, you just enforce the basically the gradient so that you get the right angle. That's basically what they say. And then if you do that, for example, you can get a relation that the tangent of theta minus pi over 2, basically this guy, is just minus of the gradient in the y direction and the gradient in the x direction, and you just implement this in your basically discretizations. And surprisingly, if you do that, it works. So this is actually quite a simple implementation. So basically what I'm trying to say is that you have options. If you can do it one way or the other. Now, going back to what Christoph was asking, we have a way to introduce multiple fluid components. How do we introduce the density ratio? Because for most systems, you want to have liquid and gas, and the density ratio is quite high, right? So in Lattice Boltzmann, this is actually a very hard challenge. So it takes a while for people to sort this out. Probably now there are maybe 5 or 6 ways that people have proposed to do this, but typically this is for a binary system. So simply for liquid and gas, and typically of the same material, right? But I'm interested in systems where they are immiscible liquids. So how do we do this? So what I'm going to do is to borrow ideas from what I told you just now. And basically what this guy did, so this is a collaborator of mine, so Ilya Karlin at ETH. So I'm going to basically marry the smart choice of equation state and free energy model, and what they call the entropic Lattice Boltzmann scheme. So I'll tell you a little bit more about the entropic Lattice Boltzmann scheme later on. Okay? Now the idea is the following. Remember the free energy diagram I showed you where there are 3 minima? And then they correspond to 3 different liquids. I'm going to take exactly the same picture, but just change the equation, basically. So my idea is the following. I can actually introduce a free energy model so that I have 3 minima. And I would like to design it so that 1 minimum sits at this place, which is actually at the gas density. So basically, I'm replacing this order parameter with the density. So I choose 1 minima to be the gas density. And then typically, if you have 1 minimum here and 1 minimum there will be the typical equation of state you might propose for a liquid gas model. This could be Carnot-Stirling, it could be Peng-Robinson, it could be van der Waals. So the idea that we have is that if you just have that, which is this piece here, you get 1 minimum here and 1 minimum there. And what we do is just introduce double well potential so that we turn this point here from a minimum to a saddle. And then we actually get another minimum here corresponding to a liquid density, but a different composition, and another density, a high density at another composition. Right? So very simple idea. I'm telling you this, so it actually works. So there are some tricks that you have to put. So for example, there are quite a few constants. And then if you are familiar with your first or second year thermodynamics, what you typically do is that you choose the constants so that the Maxwell construction, so basically at equilibrium, the chemical potential has to be the same. So you basically choose your parameters so that you get Maxwell construction. That's what you need. So those are actually the bulk free energy. So that means you have a free energy model that allows you to have 1 gas and 2 liquid components. Now we want to have surface tension, so we have to introduce gradients as before. So in this particular case, because I have 2 order parameters, I basically have gradients in terms of gradient of rho, which is my density, 1 order parameter. Or if you like, we can think about this liquid concentration, but maybe this is a better formulation. This is a gradient in rho, this is gradient in phi. This is to distinguish my liquid 1 and liquid 2. And of course, I have my cross term between the gradient in density and in phi. Okay, so that's what I need. And then of course, once you write down the free energy, you can derive the chemical potential. And then if you have the chemical potential, you can actually write down the gradient of the pressure tensor for my fluid. Right? Now, this is basically the thermodynamics. So this is quite general. So if you want to solve it with other methods, you can. But now I'm going to tell you how to solve it with Lattice Boltzmann method. Now, the Lattice Boltzmann method, I think is quite nice because it's quite simple to implement. So in Lattice Boltzmann, what distinguishes it probably with other methods is that you discretize the space, the time, and also the velocity directions. Right? So this picture here corresponds to what we call the D3Q19. So that means 3 dimensions, and there are 19 velocity directions that we have chosen. Right? So with every direction, you associate what we call the distribution function. So this corresponds to how much of the liquid is propagating in that particular direction. Right? And then what you do in Lattice Boltzmann is that you solve this very simple linear equation where you basically have 2 steps. One is the collision. So this is the new distribution function is equal to the old one plus a term that corresponds to relaxation to equilibrium. Right? And if you have a force, then you add a term that gives you this additional forcing term. So this is basically based from the Boltzmann equation. So Lattice Boltzmann simply means you solve Boltzmann equation and you discretize it on a lattice. That's basically where the name comes from. And then the streaming step simply does the following. So if you correspond to this lattice point and you have this F that is corresponding to this E1, so what streaming method does is that you move this distribution from this point to the point over there. Right? So what you do is that collision, stream, and repeat. That's all you need to do. So in the Lattice Boltzmann community, this is quite popular because it has several nice properties. One is that it's very simple to implement. Second, it's very good for parallelization because you only need nearest neighbors. And the third thing is that because typically your distribution functions fly through a straight line, boundary conditions become very easy. So if you want to put complex boundary conditions, it turns out this is quite easy to do with Lattice Boltzmann. Okay, now if you want to know a bit of the details, this parameter beta here correspond to the relaxation time, and then it can be shown that this is related to the viscosity, and this is the simplest collision term. And then the other thing you need to make sure is that during collision, you have to satisfy mass and momentum. Okay, so this is quite normal. So apologies for the advertisement. So a couple of years ago, a few friends and I wrote a book on Lattice Boltzmann method, and we have basically beginners in mind. So we actually call it principles and practice, because there are lots of example codes, basically hints about parameters to use and so forth. So if you're interested in Lattice Boltzmann method, maybe you want to have a look. Okay. Now, if you use the standard Lattice Boltzmann method, the problem is that it won't be stable if you want to reach this high density. To reach this high density, you need to do something a bit more advanced, and we use something called the entropic Lattice Boltzmann scheme. So if you compare the simplest collision scheme with the entropic collision scheme, the only difference is that we have a factor of 2 here, and we have a factor of alpha over here in the entropic Lattice Boltzmann scheme. Okay, everything else is the same. This is a particular choice of a forcing term, and we use this to implement the thermodynamics. And then you determine alpha here based on this non-trivial solution of this H equation. So basically, this is the lattice equivalent of the Boltzmann H function. And what this entropic Lattice Boltzmann scheme does is that it makes sure that the H function doesn't increase. In other words, the entropy is always increasing. Right, so it's a sensible thing to do. Okay, so this is basically how we do it. Of course, we do our due diligence. So the first thing we do is that we try to reproduce the thermodynamics. So for example, we can do a liquid droplet surrounded by gas, and indeed, we can actually reproduce different equation of states that you want. So we tried van der Waals, Carnot-Stirling, and Peng-Robinson. So this is a comparison between data point simulation and straight lines, basically the prediction from Maxwell construction. We also do what we call the bubble test, and we notice that we do get the Laplace pressure correctly. And then the other thing that we have done is that we can determine, for example, the surface tension for each of the interface, and then if we put things together, so similar to before with the liquid lens, actually the prediction between the theory and the simulation also agrees within a couple of degrees. Okay, so this is what we have done. So I'm going to tell you basically Lattice Boltzmann using basically in the more standard case, but there are actually lots of fun things you can do. So I'm just going to show you 2 things that we have tried that I think is probably a bit more advanced. So there were some simulations on curved surfaces. So we can do that as well, but we cannot do deformable surface. We can only do a curved surface, but the surface is actually fixed. So this is a case where we have 50-50, and this is the case where we have one majority, for example. So if you notice with this example here, that there is some fun thing where the droplet prefers to sit on the outside, and this is because the line energy becomes the smallest, for example, so we do capture that. So we could do that, and then one problem that we're a bit obsessed is at the moment is trying to develop model to look at elastocapillary problems. So for example, this is some simulations where you have elastic particles and you have a liquid droplet in the middle, and as you can see, it starts to spread. So this is 2 particles, this is 4, and one thing that is fun is that the liquid likes to spread, but eventually you deform the particles so much that it basically stops. Right, so I hope I convinced you that Lattice Boltzmann is quite versatile to look at these different problems. Okay, so now I'm going to focus on one particular problem. I'm going to tell you about this collision of immiscible droplets. This is my first example I want to concentrate on. This is recently accepted in PRL, so if you're interested. Now, I will start with a simulation where the 2 droplets have identical properties, except I call them liquid 1 and liquid 2, right? And then what I do is that I basically fire them off against each other, so I shoot them against each other. This is what happens if you have relatively high velocity. You see that they come together and they bounce, very similar to what you see in the experiment. On the other hand, if you use a lower velocity, you see what we call the adhesive collision regime. Okay? And indeed, if you try to look at what happens in experiments, there are cases where, I guess qualitatively it's quite similar. So we haven't tried to actually match directly with experiments because one of the problems in this community is that it seems they measure the liquid-gas surface tension carefully, but not the liquid-liquid surface tension. So obviously, if you want to simulate it, you need to know what the liquid-liquid surface tension you have to put in. Now, let's look at the case where we have non-symmetric property between the two liquids. So in this particular case, one of the surface tension, the liquid-gas surface tension, is higher than the other, considerably higher. So let me play you this movie first in 3D and then the cross-section. So the droplets come together and then they kind of oscillate. But what happens here is that the velocity is not high enough, so the droplet starts to get inside, but then it basically goes back to its thermodynamic equilibrium. So it comes out again. So you can actually see this in the two-dimensional cut. So this is exactly the same movie, except this is just the 2D cut. So it starts to oscillate. So the contact line here starts to propagate, but then it basically retracts again. Right? And then eventually it reaches an equilibrium, which is given by the Neumann triangle I was telling you before. Right? Now, what happens if we just simply increase the velocity of collision? So very similar qualitatively, but because there is enough kinetic energy, so the red droplet basically gets encapsulated. And what is interesting here is that the oscillation of the droplet actually helps. So what that means is that if you play around with the variable, the viscosity will play an important role in this problem. Right? So you can either help or discourage what we call insertive collision here. So this is the 2D cut of the same movie. So you can see this. So you see the oscillation. Whenever it oscillates like this, it helps the contact line to propagate, and eventually it meets, and then it basically gets encapsulated. Okay, so again, if you look through the literature, you can see cases where they report this, but the quality, unfortunately, is not that great. So you can kind of see similarities. So you have the interface here, and eventually it gets encapsulated there. Okay, so you kind of have to believe me, the quality is not so good. But if you're interested, you could come back later, and then I'll show you the boundary. Okay, so what's next? So what we're trying to do now is to actually talk to experimentalists to do things properly, so we can actually try to match this. But then there are cases where they have done lots of experiments. So what they do is that they play with the impact parameter. So basically whether it's head-on or it's actually colliding like this. And also changing the Weber number or the velocity. And these are basically the different things that can happen. So if, in particular, if you increase the velocity, there are some funny things going on. This is what they call the stretching separation. You can also get what they call this single reflex separation. So basically, they come together, but because the kinetic energy is so high, then this droplet basically get pinch off, basically. So I think this is a really, really rich problem to look at. Okay. So now I'm going to tell you the second example I would like to focus on. And this is to do with liquid infused surfaces. So this is the problem that David Kere and Daniel was talking about on the first day. So we can simulate this now. So let me remind you that the typical geometry is this liquid droplet sitting on this corrugated surface, but there is an oil that is infusing the corrugation. Right? So the first thing that you could do is to ask the question, what happens if you play with the contact angle of the oil? Right? And there are actually a number of wetting states that you can have depending on the oil wetting angle. So for example, if the oil is extremely wetting, both in terms of the water and also the air, you basically get this thin layer of oil between whatever and the surface. This is what Daniel and David Kere was talking about. But on the other hand, if you have chosen your oil poorly, so for example, so here you have chosen the oil-water contact angle to be larger than the critical contact angle for basically penetration of the oil, you basically get something similar to the Wenzel state. So the droplet gets basically, it's penetrating the corrugation, so that's actually bad. So typically in experiments, you basically choose these 4 states. So typically the droplet will be suspended, but either there is a thin layer of oil between the droplet or the gas and the surface, or they're actually in contact. Okay, so this is ideal because then you have no hysteresis. But in this talk, I'm going to tell you about this case because actually it's a bit richer. So I want to tell you the story about this guy here. Now, if I'm telling you that I'm dealing with this kind of system, the first thing we have to address is that how do you define the contact angle for this system, right? So typically the contact angle is basically the point where the liquid, the gas, and the solid meets. Yeah? But if you look at the system, there are many contact lines. So you have this contact line, which is the water, gas, and oil. You have this contact line, which is water, oil, and surface. And you have this contact line, which is oil, gas, and surface. Right? So we have to make a decision, how do we define the contact angle and therefore the wettability? So we have proposed that the right way to define the contact angle is what we call the apparent angle, and that is actually measured for us at this triple line here, and is measured respective to the horizontal line. Okay? Now, if we know that that's our definition, the first question is that can we predict analytically what that contact angle should be? Because in principle, we can measure the different tensions in the system. Now, to do this, to derive the effective contact angle, in equilibrium, you need to have force balance, and there are actually 3 force balances. If you look at microscopically, the force balance here, there, and there. But then if you remember your first year mechanics, if you have a big body, there are force balances everywhere. You can actually treat the big body as one body and then treat the force balance there. So you basically just assume that this is basically one thing and do the force balance there. So if you do that, you can actually say that the surface tension here is just the average surface tension between, this one is actually gas and oil, average with the bit that actually corresponding to gas and solid, because if you look at this surface tension, there is actually interface between gas and solid and gas and oil. You can also do the same thing with this guy. So you just take a simple average. So this is in a sense of a Casey-Baxter approximation. And if you plug in this definition similar to Young's angle, you end up with that. And if you simplify, we actually have a nice and tidy equation for the prediction for the apparent angle. Okay, so this is assuming this meniscus here is very small. So in that limit, basically all interfaces are basically flat. So if you want to do something a bit better, you have to take into account that the interface is actually curved. So this interface is curved, that interface is curved. And in that limit, you can still solve it. You can look at this paper if you're interested. So we did solve it. And then in that particular case, we have this rather probably less nice looking equation. Okay, so the definition corresponds to basically this guy. So it depends on the Neumann angle and also this wetting angle of the oil, basically. Okay, so we have the prediction for the apparent contact angle. So the first thing that we do, of course, is that we want to test that our Lattice Boltzmann method can reproduce this, right? So we need to make sure that the equilibrium is reproduced. So this is the comparison between simulation results and the analytical. So in red lines, this corresponds to the comparison with the full solution I was telling you about, and then the green data points correspond to the comparison with the vanishing lubricant approximation. Okay, so I guess what I'm arguing is that in general the agreement is pretty good. So one difficulty in doing this in simulation is that in practice, you actually know what all these parameters are, but you don't know what the change of pressure between water, air, and oil, air in priori. So what we do is that we do the simulation and we measure the curvature, and from that we back out basically what the Laplace pressure is. So there is uncertainty in that measurement. This is why the data is a bit noisy. But I think we are quite happy with that. So that's the static. And of course, the only reason we do simulation with Lattice Boltzmann is because we want to study the dynamics, right? So with the dynamics, this is a sort of typical geometry that we do. So we do the simplest thing, which is to drive the droplet moving across these liquid infused surfaces. So you see that we can capture the typical dynamical behavior. And these are the typical simulation geometry that we do. So maybe one thing I would like to emphasize is that we typically use what we call the quasi-3D simulation. So what that means is that the drop itself is actually cylindrical, but we have to capture the pose basically one by one, because we have to make sure that the oil can actually flow through in between the corrugation. So if you do complete 2D, it's a different system because the oil cannot pass through. It's basically being stopped by the pose. So we need to do 3D so that the oil can actually go through like this. Okay. Now, again, we do our homework. There is actually a beautiful data set by David Kere. So the red data points are actually the experiment. So what you see here is that David was actually using a series of experimental systems where he kept everything the same except he varies the droplet viscosity. So with here, with the x-axis, it's increasing droplet viscosity, but he keeps everything else the same. Okay, so these are the experimental data, and this is our simulation data. And I would say that we are quite happy with the agreement. I think it's reasonable, so we can trust our method. But maybe I'll tell you a little bit about the physics, what it actually means. So you see that if you look at the data, there are two limiting behavior. One, when it's actually pretty much flat, and then there is the bit that actually goes linearly down here. Okay, so this is actually a crossover where the dissipation is dominated within the bulk of the drop, or the dissipation is dominated within the meniscus. Right? So if the dissipation is dominated by the meniscus, basically the dissipation in this little corner here, you notice that whatever you do to the droplet, it doesn't matter. Right? Whereas if the dissipation is actually dominated by the bulk of the droplet, of course, if you change the viscosity, then if you've increased the viscosity, obviously the droplet is going to move slower. Okay, so that's basically what it means. Now, I would like to tell you a bit about, maybe in the last 5 minutes or so, about what happens if we are in this regime where the droplet and the air are in contact with the surface. So this is the data. So this is quite complicated. So please only focus on this part here first. So let me explain that. So the black line is actually the data for binary system. So just a simple liquid droplet on a smooth surface, and we just basically push the droplet and we increase the contact angle of the droplet. No slip. So there is a bit of a slip, and that comes in our case because of diffuse interface. So we have some diffusion, right? So what we notice is that the velocity goes up with the apparent contact angle. So what it means is that the more the droplet bulge up, the faster it moves, right? Now, if you look at what happens with the liquid infused surfaces, you see similar behavior, where typically if we have the same system when we increase the apparent angle, and the way we do this is by playing around with this Neumann triangle. We notice that if you look at the red, green, and blue lines, they also increase monotonically. Yeah? But what's the difference between the red, blue, and green lines are basically this oil angle over here that I have changed. Right? But what is interesting here is that if you look at what happens at high apparent angle, if you want to make your droplet move faster, you should actually use an oil which is more wetting. Okay, makes sense? However, if you're looking at the system at low apparent angle, actually you should do the opposite. If you want to make your droplet move faster, you actually should use an oil which is less wetting. Right? So there is a crossover, and now I would like to explain why this is. Okay, now let's concentrate on what happens over here. Now, if I take this basically 3 droplets with very similar apparent angle, and I'm just looking at the instantaneous velocity as a function of time, these are the data. Okay, so you notice that the velocity of the droplet oscillates, and then the blue one oscillates a lot more than the red one. Okay, so this is a typical signature of a slip-stick motion. Okay. Now, we actually have a movie that can show you what that actually means. So this is a slip-stick motion. So whenever you see a decrease in the instantaneous velocity, this is because typically there is spinning, and whenever the velocity goes up, that's because it depends at the back. Okay? So you get the spinning, the pinning, and it does make sense that if the oil is more wetting, the pinning is less. Right? So this is what we notice from this data. Right? So more wetting, pinning is less, droplet moves faster. Agrees with this data. And what is interesting is that if we actually push the droplet with different forces, so if you like, you basically tilt your experiment more and more and more and more, what we notice is that these 3 cases actually fall onto the same master curve if we plot it against BO minus BOC. Right? So BOC is the critical bond number at which the droplet starts to move. In other words, this corresponds to the pinning force that the surface is acting on the system. However, if you look at what happens here, the first thing you notice is that the oscillation is a lot less. So that basically means that the pinning is weaker, actually much weaker. And also, if you plot the capillary number against BO minus BOC, you cannot actually have this data falling onto a master curve. And actually, if you look at what is BOC, they are more or less the same. You can't really distinguish them. So it means pinning is really weak, right? So now the question is, what is the reason that for this low apparent angle, the more wetting oil results in droplet moving slower, right? So that's what we want to answer. So to do this, of course, the nice thing about simulation is that you can change the geometry to help you give insight. And what we have done here is that let's imagine what happens if we just completely remove the pinning, which we can do. So the geometry that we are going to look at is basically this. So we basically put a water droplet and basically some oil at the front and at the back, but we remove the corrugation, so there is no pinning. And one thing you notice is that this is actually comparing droplet B and D, so it corresponds to this droplet and that droplet. So what you notice is that the apparent angle is basically the same, but the wetting angle is different. If you stare at the droplet, the shape of the droplet is very similar, but what is different is the shape of the meniscus, right? So before, when I compare this against David K. Ray's data, I tell you that dissipation at the meniscus is important, and that's basically what happens here. Okay, so we can actually derive a simple scaling analysis. So what we can say is that this is basically the input of energy. This is dissipation. This is simple scaling law. This is to do with the droplet. This is to do with the meniscus. And then if we just think about how they actually scale, so I would argue that the droplet velocity gradient scales as the typical velocity over r, the size of the droplet, and then the area of the droplet scales as r squared. Whereas for the lubricant, I would argue that the gradient in velocity scales as the velocity divided by this height here, but then the area scales as the area of this triangle, which is h times L. Okay. Now, if you just basically manipulate the equation a little bit, you notice that the velocity depends on the force and also on this aspect ratio of this guy here on the meniscus. And indeed, if we compare our simulation data and the simple theory, they actually fit quite nicely. So this is plotting velocity as function of this aspect ratio, which is basically just this thing here. Okay. Now, the last thing I would like to do, maybe in the last 1 minute, is that now that we have the data, one thing we're trying to understand, this is a question that have puzzled many people. If you have a liquid droplet on the surface, when it moves, does it roll? Does it slide? Does it tongue thread? Does it do whatever? So we're trying to analyze this, and this is some preliminary data that we have. So of course, what we can do is to actually extract the droplet velocity inside the droplet, and then we can convert this to the drop center of mass, and we can compute the residual vorticity, and from this we can actually define what we call the percentage of rolling. If you like, this is a ratio between the velocity corresponding to rolling and to a translational motion. What is interesting here is that if you look at the typical behavior for binary system, this is increasing with apparent angle, but for liquid infused surfaces, it seems that there is actually a plateau. So we haven't quite understood this. But what we think happens is that if the droplet is moving, there is actually a nice behavior that is to do with Landau-Levitch film formation, right? This is, I think, Shahriar spoke a little bit about this, and also Dan Daniel spoke about this. So basically, as the droplet is moving, you actually have the oil creeping through, so effectively the droplet is lifted, right? So this is, we think, what makes the rolling percentage to go down at this high apparent angle. Okay, so I think I'm probably running out of time, so I'll skip the bit about the contact line motion. Maybe I will just tell you one thing, that we did some systematic analysis because there were two scaling laws that people have proposed, one by Jack Bean, Peng-Tang Ye, and James Fang, which is actually this this different scaling law. And there's also another one by Julia Yeomans and Andy Bryan, which is this bit. So all I wanted to say is that actually both scaling laws are correct. It just depends on where you are in your simulation. So with that, I would like to conclude that I hope I've convinced you that the Lattice Boltzmann method is versatile, so we can do many things with it. And also that ternary fluid system is very fun, very exciting, and hopefully some of you will work on that in the future. Thank you.
Problem, if I well understood, you saw the three fluids, I think the two fluids with the gas. I would have expected to have a small level of air entrapped by the impact. Can you see it? Or?
So we did try, but I think we can't because we have a diffuse interface model. What we notice is that I think probably our resolution is not fine enough. So what we need to do is
I
to,
mean, the bubble would be of the size of the diffuse interface. The diffuse interface is probably very large compared to
yeah,
physical.
yeah. So what we need to do is to increase the resolution. Yeah, correct, correct. But that will be something that we tried to look, but we couldn't find it, at least so far.
So my question is about error and accuracy. So
Yeah.
there's three related questions.
Yeah.
One is you have an underlying mesh. How does that affect things? Two is the relationship between Boltzmann and continuum mechanics. So is there a Kutzen number or something hanging out there?
Yeah.
Okay. And the other is how this all relates to the parameter in your original phase field left model. So it's a fusion parameter. What conditions?
Right. So this is
I
a.
have no feeling for how good this is.
Yeah, so this is definitely a hard question. So, yeah, so in terms of accuracy, I think all the scheme we have typically used, they are second order. But of course, with second order, what you need to know, sorry? In space, yeah. And then the question is, of course, what is the prefactor, right? And that prefactor depends on the choice of parameters. So we typically choose the parameters so that if we look at the spirit velocity that we get, that's typically less than 0.5% of the actual typical dynamics we're interested in.
Second order converging to what?
So basically, if we, let's say we have the system, and then we basically increase the resolution.
What do I converge to?
So in our case, typically we look at the case with the highest resolution. That's typically what we do.
Are you converging to Navier-Stokes?
Oh yeah, the scheme converges to Navier-Stokes.
When you're saying second order, you mean you're converging?
Yeah. Have I missed one of the questions?
Well, I'll ask you later.
Okay, yeah. Okay, we can discuss that, later. Yeah.
So, I mean, one problem I see with ternary fluids is actually choosing the free energy. I mean, you kind of said you have a polynomial and you base the millimeter. That's kind of, in a sense, the simple thing. But one problem which I think should arise or could arise is if you have, let's say, this case where you have a gas which you want to be separated. You basically just have one boundary with the gas, and then there is another boundary between the two liquid phases. How do you prevent the gas phase from appearing exactly between those two phases? If you have a binary system, it's clear the interface has to be pure, but then you can have diffusion into this.
Yeah.
It's for the system easier to kind of just escape a bit into the third phase.
Yeah, so I think that's an excellent observation. So our choice of free energy potentially has that issue. So we haven't noticed that. Sorry, let me just go back to the plot that I was showing earlier. Yeah, so here we have chosen two other parameters, right? So one is to distinguish the liquid, and the other one is to distinguish the density. So you notice that the gas actually sits over here, which is basically a mixture between the two liquids. So if you want to avoid that, what you need to do is actually a third dimension, so that effectively the gas is a different component. So we have to think about how to introduce that. But I think it's possible. One has to think carefully, but I think it's possible. We haven't done it, but I think it's feasible.
Maybe we should talk to you. That's the best thing I think.
Okay.